Hello everyone, my name is MASUDA from Kawa University, Japan. Today, I will present my research titled Accelerating HNSW in lag, a dynamic cache method based on topic biased access patterns. Here is the agenda for my presentation. First, I will explain the background of lag and HNSW. Second, I will describe the problems we face and our approach. Third, I will introduce our proposed method, TCHNSW. Fourth, I will show the evaluation results and discuss them. Finally, I will conclude the presentation. First, let me introduce the background. Recently, large language models, or LLMs, are advancing rapidly. However, LLMs sometimes lack specific knowledge. To solve this, RAG, or retrieval augmented generation, is widely used. This is a basic RAG architecture. When a user asks a question, the system searches for relevant documents in the vector database. Then, it combines these documents with the prompt. The LLM generates an answer using a context. Therefore, the performance of RAG heavily depends on the vector search performance. If the search is slow, the user will be stuck waiting. Next, I will explain the core algorithm used in vector search. We focus on HNSW. It is a popular graph-based search algorithm. As shown in the figure, HNSW has a hierarchical structure. Layer 0 is at the bottom layer, which contains the full graph with all data nodes. The upper layers contain only a subset of these nodes. The search starts from the entry node as the top layer. It traverses same layers, neighbors, and moves down layer by layer. First, it does a quick, rough search at the upper layer. Then it moves to the lower layers for a more detailed search. There is an important parameter called EF. A higher EF values checks more neighbors' nodes. This contributes to better accuracy, but it spends more time through. So that HNSW has a major challenge. It consumes a major amount of memory as the data scale increases. It is difficult to store all data in memory for large-scale RAG. There are two existing solutions, but they have problems. Solution 1. This solution is using MEMMAP, or memory mapping. This keeps data on disk. It is useful for low memory environments, but its response time becomes significantly longer due to disk I/O bottlenecks. Solution 2. This solution is PQ, or quantization. This compresses the vector data. It reduces memory usage, but it degrades search accuracy in lag. Accuracy is critical. Therefore, achieving fast, accurate, and memory-efficient search is very difficult. Specifically, since RAG requires high accuracy, we must find a way to reduce I/O while utilizing the MEMMAP mode. To solve this problem, we focus on topic bias. In an organization, search queries are not random. They have category locality. This bias varies by user, department, and time. For example, in September, the HR department searches for new hire training. Meanwhile, the development department searches for product Y specs. However, in December, the HR department might search for performance reviews, and the development department might search for product X specs. We call this topic bias. Our approach exploits these access patterns to optimize disk I/O. Based on this idea, we propose a method called Tiered Cache HNSW, or TCHNSW. Our method uses a tiered cache system. This method requires the dataset to be categorized in advance. The system identifies hot topics or categories from recent search history. Then it dynamically caches the vector data groups of these categories. Frequently accessed categories are stored in Tier 1, which is the fast memory. Less frequently accessed data stays in Tier 2 or Tier 3 on the disk. The key feature of our method is that we do not modify the graph structure. We only manage the storage location of the vector data. This ensures 100% search accuracy compared to conventional methods. It adapts to changing topic dynamically. This slide shows the system design. We added new modules to the conventional HNSW search. To explain their role simply, the cache management modules act as the brain, and the data management module act as hands. On the left, the cache management module. This module manages search history and category information. It decides which node data to cache next. It uses a lookup table and access history to make this decision. On the right, the data management module. This module acts as hands that hold and update the actual cache. When a query comes, it attempts to respond from the cache. If it is a hit, it returns the data from the fast cache. If it is a miss, it accesses the slow disk via conventional method. This modular design separates the decision making from the data access. Next, I will explain the evaluation setup. We evaluated the effectiveness of TCHNSW in two main objectives. First, we confirmed the cache operation via resource utilization monitoring. Second, we verified the cache effectiveness by comparing response times. To do this, we implemented our method on Quadrant, a popular vector database. We use a categorized English Wikipedia dataset and use BGE M3 to embed the dataset into 1024 dimensional vectors. For the environment, we limited the Quadrant server memory to 8 GB and allocated 3 GB for the TCHNSW cache size. We tested EF values ranging from 64 to 512 and tested dataset size ranging from 1 million to 6 million vectors. We compared response times in 3 scenarios. Scenario 1 is conventional. This uses map with random queries. As defined in the footnote, random means queries are randomly selected from the entire dataset. There is no topic bias. Scenario 2 is also conventional, but here we use category queries. This means queries are limited to a specific category. In this experiment, we use 3 categories: academic disciplines, politics, and engineering. Scenario 3 is our method TCHNSW. This uses our cache system with the same category restricted queries used in scenario 2. We tested with 5,000 queries in each scenario. First, we verified the cache operation. These graphs show resource utilization over 30 seconds. The x-axis is time. The y-axis is utilization percentage. The orange arrows on the right indicates that lower is better for I/O utilization. The blue and orange lines representing the conventional methods. The blue line is map with random, and the orange line is map with category. They show stable, low CPU usage, but the I/O is almost 100%. This means the system is I/O bound. The disk is the bottleneck. Now, focusing on the green line for TC-HNSW. At the beginning, I/O spikes and CPU drops. This is a cache loading phase. After that, the I/O drops significantly, and CPU usage increases to about 35%. This means the cache is working. The system is processing data in memory, not using the disk. From here, I will show the response time result. The x-axis represents the dataset size in millions, and the y-axis represents the response time in seconds. The orange arrows indicate that lower is better. This slide shows the baseline performance using conventional map with random queries. With no topic bias, the performance degrades rapidly after 3 million vectors. The red line, which represents EF512, at 6 million vectors, the response time exceeds 1.4 seconds. This confirms that map is very slow for large dataset with high accuracy settings. Next, let's look at the result for the academic resprints category. Comparing the three graphs, baseline, conventional with category, and TC-HNSW, we see a different result. In this case, TC-HNSW did not show improvement. This overhead of about 6% makes the response time around 1.4 seconds, which is nearly the same as the baseline. This is because the academic disciplines category has a weak topic bias. It is a very broad category, so the cache hit rate was low. Next is the politics category. This category has a clearer topic bias. For the conventional method shown in middle, the response time is 1.01 seconds. It is faster than the baseline because the OS page cache works partially for categorized queries. However, looking at TC-HNSW on the right, the response time dropped to 0.74 seconds. This is a 27% improvement compared to the conventional method. And it is a 49% improvement compared to the baseline. This shows that our tiered cache is effective. Finally, we tested the engineering category. This showed the best performance. In graph 3, the red line demonstrates this significant improvement. The response time is only 0.49 seconds. The baseline was 1.45 seconds. This is a 66% reduction in response time. Also, remember that we are using EF equal 512, so the accuracy is high. This result proves that TC-HNSW is ideal for RAG when a strong topic bias exists. Let's discuss the finding. First, we confirm the caching behavior through CPU and I/O utilization. Second, TC-HNSW successfully mitigates the map I/O bottlenecks. It is especially effective for large-scale and high-accuracy searches. We found that it can reduce response time by 30% to 60%. Most importantly, it maintains 100% searches accuracy because we do not modify the graph. The conditions for success are 1. A clearer topic bias must exist. 2. The dataset size must exceed the memory capacity, causing data access. I will conclude my presentation. As a background, RAG uses vector databases. but large-scale search suffer from slow response times. To solve this, we propose TCHNSW, a dynamic tiered cache based on topic bias. The result shows that it accelerates search without degrading accuracy. It provides a practical path for memory-constrained RAG systems. For future work, we plan to explore dynamic parameter optimization and automated topic classification. Thank you very much for your attention. Do you have any questions?
Thank you so much, Ray. Are there any questions from Ray? Okay, so thank you so much, Ray. With that, we are going to proceed with the next paper. The next paper is AI cache, a caching method applying application inference targeting file sharing servers. The paper is by Keiichiro Higashihara, I hope I pronounced the name correctly, and their colleagues. Keiichiro, if you are available, please feel free to share your screen and start the presentation.
Can you see my screen sharing?
Yes, I can see your presentation.
Thank you.
Please start whenever you are ready.
I'm Keiichiro Higashihara. I belong to the Kagawa University in Japan. I'd like to talk about AI cache, a caching method applying application inference targeting file sharing servers. Here is the outline of my presentation. First, I will talk about the background. Second, I will describe the challenges and the proposal method. Third, I will explain the system design and the implementation. Then, I will show the evaluation and the discussion. Finally, I will conclude my presentation. First, NFS server only accepts requests from clients regarding file access. As shown in this figure, when a client reads a file stored on an NFS server, the client sends read call procedure to the NFS server. According to it, the NFS server returns read reply procedure. The crucial point here is that NFS server cannot know what application are running on the client. It only sees read request. Next, I will explain NFS server caching. Caching on the client side and server side is applied to boost NFS I/O performance. In this research, we focus on the server-side cache. The server-side cache is a general-purpose mechanism. It is a page cache. Whenever a file is read, the data is put into the page cache. This reduces I/O latency and improves throughput. It provides scalable performance across various workloads. On the other hand, this approach is not optimized for the specific application I/O patterns. Applying caching optimization for specific workloads is difficult because NFS server cannot identify client applications and predict future I/O patterns. To address this issue of not knowing applications, an application inference method was proposed in a previous study. This purpose is ransomware detection. This method can infer multiple applications running on clients. It is based on the hypothesis that file access patterns observed on file sharing servers exhibit temporal periodicity. As you can see in the bottom figure, the system consists of three processes: acquisition, analysis, and inference. By analyzing packet captures, it can identify the running application. The next slide describes the challenges. As I mentioned previously, the NFS server cannot identify applications running on NFS clients. Therefore, it is forced to use a general-purpose cache. This leads to suboptimal performance for specific workloads. Manual tuning is possible, but it is static and unsuitable for changing workloads. So, we focus on the application inference method. Our challenge is applying the inference method to the optimization for NFS servers. Based on this challenge, we propose AI cache. If we can automatically identify applications on NFS servers, we can dynamically apply a caching method optimized for a specific workload of applications. Application inference method is proposed for security. Although, in this research, we aim to apply not only to security, but also to caching. AI cache is a caching method for NFS that applies application inference method. This slide shows an AI cache design. To verify the effectiveness of our approach, we designed and improved a proof of concept system. When a specific application is inferred, the system reads ahead the entire file. The flow is as follows. First, the NFS server receives an I/O request from a client application. The server forwards the I/O pattern to the inference module. Then, the module analyzes the pattern, infers the application, and calls the read-ahead module. Based on the inferred application, the RA module executes read-ahead process. Finally, the NFS server returns the data. If the data is already cached, the server responds immediately. I present the POC system implementation. Its overview is shown on the left side. This system is implemented in NFS Ganesha, which is the user mode file server for NFS. We added two processes to it, a startup process and a new RSet. The startup process is added to FSAR MD cache. FSAR stands for File System Abstraction Layer. When read call is invoked, the startup process is called. Then the application inference module launches. The module returns inferred result to NFS server. The RSet receives the result. If read-ahead is required based on the result, it reads the target file to the end. We implemented the application inference module as external module. This module infers applications when it receives startup instruction. From the next chapter, I evaluate AI cache POC system. AI cache POC system is evaluated in the following environment. The evaluation assumes an environment where the NFS server mounts a disk. We set the I/O scheduler to none and disable I/O merging to minimize scheduling effect. In this evaluation, the NFS client runs the application on files stored on the NFS server. The application uses Vim and Emacs. They are the same as those in the related work. We conducted the evaluation in two steps. First, we verify the application inference. We check the DTW distance and the inference probability. The DTW distance indicates the similarity between waveforms. A larger DTW distance means the waveforms are more dissimilar. Second, we evaluate the cache effectiveness compared to the no read-ahead case. We use two metrics. First, the overall client-side throughput against file size, which indicates the overall performance improvement of AI cache. Second, the transfer time as a ratio relative to the cache miss, which shows how much speedup has been achieved by AI cache. In addition, we measure the disk I/O throughput over time to confirm that AI cache was operating as intended. First, I describe the result of preliminary evaluation. The figure in the upper left shows the DTW distances. The horizontal axis is the test data. The vertical axis is the ratio of the DTW shortest distance relative to the baseline application. The left figure shows the result for Emacs, and the right figure shows the result for Vim. For all test data, A DTW distance difference of at least 1.3 times was observed. These results indicate that each application has distinct characteristics and temporal periodicity. The table in the bottom left shows the application inference result. The executed applications were BIM and Emacs. Their execution patterns fall into 4 categories as shown in the table. When loading a file in Emacs, over 91% of cases were correctly inferred. Their loading file in BIM, over 85% of cases were correctly inferred. This shows that inferring application in this evaluation environment is possible. Next slide shows performance of our proposal method. Figures plot the overall throughput against file size. The horizontal axis is the file size. The vertical axis is the throughput. The file size was set to 100 MB as a baseline and increased by power of 2 up to 3.2 GB. In the left figure, the throughput for cache hit is about 110 MB per second. Where AI cache is used, the throughput for 100 MB file is likely that of the cache miss. However, as the file size increases, its throughput approaches the level of a cache hit. In the right figure, the Emacs result was similar to the left figure. In some cases, the throughput gap between AI cache and cache hit is close to 3 MB per second. Figures plot the transfer time as a ratio relative to the cache miss. The horizontal axis is the file size. The vertical axis is the ratio. In the left figure, for 100 MB file, AI cache reduces the time by about 5% compared to a cache miss case. As the file size increases, the AI cache transfer time becomes close to the cache hit time. For 3.52 GB file, it reduces the transfer time by about 42% compared to the cache miss case. In the right figure, the Emacs result was similar to the left figure. For 3.2 GB file, it reduced transfer time by about 41% compared to a cache miss case. Figures plot the disk I/O throughput over time. We use BLK trace and BIM. The horizontal axis is elapsed time. The vertical axis is the throughput. AI cache reduces total I/O time compared to a cache miss. In the left figure, the time taken to read an 800 MB file is reduced by 4 seconds. In the right figure, the time taken to read a 3.2 GB file is reduced by 27 seconds. Specifically, the AI cache throughput was initially like the cache miss case. However, after a brief period, it is increased and established at a rate slightly above 135 MB per second. The Emacs result was similar. AI cache reduced the total I/O time. We observed an increase in throughput mid-transfer. This confirms that the AI cache was functioning effectively. Based on these results, I would like to discuss the findings. AI cache infer the application and read ahead the file data into the page cache. This saves time required for file reading from disk and improve overall read efficiency. The effectiveness was particularly pronounced for the large files. This is because the effectiveness of read ahead outweighs the inference overhead. On the other hand, for small files, reading a file is faster than inferring. Therefore, read ahead cannot be performed, and if cases of incorrect prediction occur, unnecessary data may be cached. From these considerations, the following can be inferred. Incorrect prediction may result in no performance gain. However, the POC results show the read performance improvement. Finally, I will conclude my presentation. First, regarding the background, the server-side cache is a general-purpose mechanism applying an application inference method to the cache optimization was our challenge. To address this, we propose AI cache, a caching method for NFS that applies application inference method. As for the result, we achieved improved I/O throughput. Specifically, we reduced the transfer time by 42% for 3.2 GB file compared to the cache miss. Thus, we demonstrated the effectiveness of the POC system. For future work, we plan to proceed with further implementation and explore more effective caching method. Thank you for listening.
Thank you for your presentations. Are there any questions from Keiichiro? Okay, thank you so much. Very nice presentation.
Thank you.
Let us proceed with the next paper, adaptation and